Yes.
Okay, fine. Now, next part. Uh, what we learned in the previous slide is the macroscopic approach, right? And now we will define few terms like, let us take the first one as the density. So we will define this term macroscopic property, the density of the fluid, right? So up till now you must have seen the how we define the density. What is the approach you have used up till now? So you might be saying simply density rho is nothing but mass per unit volume, right? Correct? So this is how you have defined density. Right from your high school, you know this is the way how we define the density, correct? Hello?
Yes, sir.
So if you go back to this slide, and we talked about this cube having 25 dimensions, right? And the volume covered in this cube is 10 raised to, or the number of atoms present in this volume is 10 raised to 20, right? Now I am going to talk about that in this the slide as well. So if you plot this delta m by delta v, right, on the y-axis here, and there is one limiting volume, delta v dash, which is this volume, and what you are plotting on the x-axis is delta v, the small volume. So when I say delta, it means small, right? So when I'm defining density using the limits, this is mathematical definition of density, how you define it. So I will define it as a rho is equal to limit delta v tends to delta v dash delta n by delta v, right? So what is this delta n, delta v, all that stuff is written here. So consider you have a system like this, and out of this system you are taking a small elemental volume delta v, which has mass, small elemental mass, which is delta n. So this is small part of this system, entire system I have taken, right? And now I am defining what is the density for this, right? So using the limits, I can define it in this way. You can note down this. Rho is limit delta v tends to delta v dash delta n by delta v, where this delta v dash is called as a limiting volume. The limiting volume. Now the value of this delta v dash, in case of liquids and in case of gases at atmospheric pressure, this value is around 10 raised to minus 9 millimeter cube. Note down this. So the limiting volume is equal to 10 raised to minus 9 millimeter cube. So can you imagine this dimension 10 raised to minus 9 millimeter cube? It's very, very small volume, right? Very small volume. So what is plotted in this graph is this delta m by delta v on the y-axis, and on x-axis we have the delta, right? And this shows how the density varies, right? So for example, you can see there is one dotted line here. So this zone is called as the domain of molecular effects. It means you have to take into account what is happening at the molecular level if your volume, selected volume, falls in this region. Get me or not? So if your selected volume is less than this limiting volume delta v dash, then you have to take the molecular effects into account. Can you or not? Is it clear?
Yes, sir.
I repeat, if your selected volume is less than the limiting volume delta v dash, the molecular effects are going to be dominant one. You have to take this into account, right? And if your selected volume, let us say, is more than the limiting volume delta v dash, then we can say that the concept of continuum is valid. And now what is this domain of continuum? You will see on the next slide. But from this slide, you just understand density is defined using this expression, that rho is limit delta v tends to delta v dash delta m by delta v. Clear? And pay attention to this graph. So from this point onward, you will see that the density is more or less, it is like a horizontal or the constant one, right? So if you refer the standard textbooks, maybe some foreign other books, you will find there are some slight wavy curves like this, and then more or less this density is same. It means if you define density rho, considering the domain of continuum, means on this side, so this can be defined simply as mass per unit volume. I can simply say it like this, but same is not valid when I'm talking about this zone, the domain of molecular effects. So here we assume that the mass is continuously distributed or uniformly distributed throughout the passage, you can say. This is not true in this case. So there is some kind of discontinuity when we talk about the molecular effects. Now, what is that discontinuity, or what is that uniform distribution of the mass throughout the passage? That is in the next slide. Now, can I go to next slide?
Yes, sir.
Okay, now we'll talk about the concept of continuum. So what do we mean by continuum? So I'm going to project maybe 2 bullets here. You just read one by one and try to understand what these 2 bullets say, and relate these 2 bullets to previous 2 slides. One with the definition of density using the limits, and one diagram before that, that was the cube having 25 mm dimensions. So we normally are concerned with the volumes that are very large compared to molecular dimensions, and with time scales that are very large compared to intermolecular collision frequencies. Now imagine you have a tank like this, and we are talking about the volumes which are selected are very large. So this is the large tank, let us say, and even if I am taking the volume, suppose I want to define what is density of the air maybe here in this tank, right? So I may consider this entire tank as a volume, right? Or if I, even if I say some region like this, if I select, and if I try to define what is the density here, right? So still this volume selected is large, very large compared to your delta V dash. Now what is the delta V dash? It was the limiting volume, 10 raised to minus 9 millimeter cube, such a small volume. So if you take any what you can say, the system which you come across in daily life, no? That system is going to be, or the volume of that system is going to be large compared to this limiting volume delta V dash. This is what the first line says. Compared to even the molecular dimensions, it is very large volume selected. So your molecules may be like this. Now this is also exaggerated view, but the volume you have selected is very large compared to even the molecular dimensions, right? And with time scales, they are very large compared to intermolecular collision frequencies. So the molecules which are here in the volume, they are interacting with each other. The collision of the molecules is taking place inside, right? So your selected volume is such a high volume that even these things can be ignored. The intermolecular collision frequencies, they can be ignored. That's what the first. Now look at this second. We deal with very large number of molecules. We deal with very large number of molecules that interact extremely often during the observation period. So in this tank, n number of molecules will be there, right? And they are interacting with each other, they are colliding with each other, they are also colliding, or they are also striking on the surface of this tank, right? All this is happening, and this is intensive, right? So we deal with very large number of molecules. Just to explain this, what we mean by large number of molecules is the limiting volume we talked about, delta V dash. This contains number of molecules somewhere around 3 into 10 raised to 7 molecules are present in this small volume. Such a small volume, we have this number of molecules present, 3 into 10 raised to power 7. Now imagine how many molecules will be there if I am selecting the entire tank as a volume. So that number is going to be huge. So that's why this line, we deal with very large number of molecules that interact extremely often during our observation period, right? So we sense this system as a simple uniformly distributed mass in the volume, and we call this as a quantity. So the whole system, we assume that this mass or whatever the number of molecules are there present in this system, so this mass is distributed uniformly throughout this space. Throughout this space, this is what we assume. Is it clear? And this is nothing but the concept of this uniform distribution of the mass throughout the passage. We call this as a continuum. So rather, we should call it as a fluid continuum. Fluid continuum. It means simply we say that the whatever fluid is present in your system, it is continuously distributed throughout this passage. So mass is distributed uniformly. Is it clear? Now this is possible when you have a very large number of molecules present in the system, and it means when you select the volume which is very large compared to the molecular dimensions, in that case only this is true. Are you getting my point or not?
Yes, sir.
Yes, sir.
So now if you go back to this definition, this chart, you will come to know. See, the concept of continuum is valid beyond this volume, right? So what might be happening if you are in this zone? The mass is not distributed uniformly throughout the passage. So for this case, the scenario might be something like this. You have the molecules which are far away from each other, or hardly 4 or 5 molecules are there, something like this kind of situation, right? So this is not uniformly distributed. So it is quite possible that if I try to find out what is the density in this zone, rho, it might be different. If I try to find out what is rho here, density, this may be different, right? So why this discontinuity is there? Because mass is not distributed uniformly. So that's why you will see these two curvatures are given for the same problem. So it is something like this. The density will be fluctuating like this, and from this point onward, you will find that the density is constant, or you can simply define density as mass per unit volume. So the straightness of this line indicates that mass is distributed uniformly. Clear? I hope it is clear now. What is the concept of continuum? Now can I go to next slide?
Yes, sir.
Yes, sir.
Now we'll define a few more terms, like what is the thermodynamic property. So what we mean by property, you must have studied in physics also, right? Just read the definition and it is clear. So what is property or thermodynamic property? It is a macroscopic characteristic of your system. Now what is macroscopic? Means we are taking large number of molecules together and we are defining what is density, right? So in this system, let us say gas is there. So I am not defining what is density at this position or density at this, something like that. I am taking large number of molecules together and I am simply defining density, right? So density can be thought of as a macroscopic characteristic of your system, right? So the quantities like mass, volume, the energy, the pressure, right? The temperature. For all these properties, you can have a definite value. Means you can assign a definite numerical value at a given time without the previous knowledge of the how your system has behaved. So without the history of your system, you can define, or you can simply put some value for that quantity. So that is nothing but the property, thermodynamic property of the system. For example, we know that the this pressure let us say the atmospheric pressure. How we denote the atmospheric pressure? We say it is 1 atmosphere. So we can use this number 1 atmosphere at a given time t, right? So we can assign this kind of values for this property, which is pressure. So pressure is the macroscopic characteristic of your system, and then it must be called as a thermodynamic property. Is it clear? What is property? You can assign definite value for it at a given time. Next definition, what is state of your system? So what is state? So state refers to the condition of a system. Condition of a system. And this is described by the properties of your system, right? So since there are normally relations among the properties of the system, so one of the relation you already studied in physics, you may be knowing this: PV is equal to MRT, or PV is equal to nRT. This kind of equations you have used, right? So what this shows is the relationship between the properties of the system, right? Pressure, volume, mass, the temperature is there, right? So since there are normally relations among the properties of the system, the state of one can be specified by providing the values of a subset of the properties. Now, what we mean by state can be defined by providing values of a subset of the properties. And once you know those minimum properties, all other properties you can find it from these properties. Now, for example, so what we mean by this? So let us say you have this kind of a plane, XY plane maybe. This is X and this is Y, XY plane. So how many properties are required, or the coordinates are required to define the position of this dot here? So what are the coordinates required to define the position of this dot? You simply require the X coordinate and Y coordinate. So these two minimum properties are sufficient to locate this dot on the XY plane, right? We know this. So similarly, in case of the thermodynamics, when you define thermodynamic state of your system, you will come across maybe 7 to 8 properties of the system. However, not all 7 and 8 properties are required to define the state of the system. Out of this set of 8 properties, you can take minimum two properties, and still you will be in position to define what is the state of the system. For example, if I know what is the pressure and volume, then I can simply draw the PV diagram and simply put this dot. I know the coordinates, the pressure and volume here. So I have located the position or the state of the system, and all other properties, maybe the temperature or the density or maybe the internal energy, all other properties can be calculated or can be found, provided I know minimum two properties here. That is what meaning of the thermodynamic state is. So in nutshell, what I'm trying to say is, to define thermodynamic state of a system, you need at least two coordinates or at least two properties. Is it clear?
Yes, sir.
Now the next, the process. Now what do we mean by the thermodynamic process? So we'll read the definition. So when any of the properties of the system changes, the state changes, and the system is said to undergo a process. I repeat, when any of the properties of the system changes, even if a single property changes, that will be considered as the change of state. So when any of the properties of the system changes, the state changes, and the system is said to undergo a process. So a system is said to be at a steady state if none of its properties changes with time. So here we have defined steady state process also. Steady state process. So suppose you have the system which is at the initial state, let us say here. So forget about this scale. This may be x, y, any coordinates. I am just showing it for the explanation purpose. So even if the single property of your system changes, then the next state of the system will be different than this I, right? So let us say your next or the final state is this one. So your system has changed its state from initial state I to final state F. So the properties at this level are different, and at this they are different, right? And this is nothing but the process. So you can say that when the moment your properties of the system or a single property of the system is changed, you can say that the process has occurred, you can say, right? And now what we mean by steady state process. So imagine you have flowed through a pipe. So suppose water is flowing through this pipe. So this is the inlet and this is the outlet. So in, out, right? So whatever is entering the pipe, the same mass is going out of the pipe. So what remains inside the this? Suppose if I say this is your control volume, then the mass within this control volume is same all the time, or not, or constant. It is not varying, right? So if the properties do not change with respect to time, we call it as a steady state. Means suppose if temperature is there, so this temperature is not changing with respect to time, so this change is zero. There is no change in temperature with respect to time, then I will say it is a steady state, right? So in similarly for this case, when the mass is not changing with respect to time, so there is no change in mass with respect to time, then I am going to call this as a steady state process. Is it clear? What we mean by steady? So steady has something to do with time. We are going to talk about these kind of processes in detail in the coming lectures. But for timing, just remember, if any of your thermodynamic property is not changing with respect to time, then we call it as a steady state. Now, what do you mean by extensive and intensive properties? You must have studied in physics again. Now, what is extensive property?
Properties which depend on the amount of matter.
Which depend on mass, we call it as an extensive properties, right? Now look at the definition, how it is defined. So property is called extensive if its value for an overall system is the sum of its values for the parts into which the system is divided. So what we are going to do is we will take a system, we will divide it into equal parts, and then we will check whether this definition is correct or not, right? And the examples of extensive properties are given, which is the mass, volume, and energy. You may be knowing this. I did not have to explain this much further. So here are a few points or the bullets about extensive properties. So extensive properties depend on the size or extent of the system. So how small or how large your system is, on that part the extensive properties will depend. For example, mass. So for smaller systems, we will say that the mass is small for the fixed component, I'm saying, and for larger it will be high, right? Then we have the second point. The extensive properties of the system can change with time. For example, let us say mass is your extensive property. So this can change with time. So dm by dt means rate of change of mass. This may occur. So it is possible that the mass may change with respect to time. Rate of change of mass. So similarly, the temperature may change with respect to time. So these properties change with respect to time, right? So here we are talking about the mass. That's why I put this reason. Fine. Then many thermodynamic analysis consists mainly of carefully accounting for the changes in extensive properties such as mass and energy. So there is some background noise. Mute yourself. Okay, fine. So we'll be talking about the changes in mass and energy with respect to time. So every now and then you will come across these terms, rate of change of mass and then the rate of change of energy like d by dt or d by dt, something like that. So these rate of change of mass and energy we will talk about. Now what is the intensive property? Which are independent of mass, right? Look at this example. So we have a system like this, having the properties, initial properties as a mass, volume, temperature, then the pressure and the density. Now we will divide the system into two parts using this dotted line. So you will see that the mass will be half now. The volume will become half. The temperature will remain as it is because it is independent of mass, right? Pressure will remain as it is, and even the density will remain as it is, right? So these three are intensive properties, independent of mass, whereas these two are dependent on mass. So these are the extensive properties, right? So if I add one more term, let us say specific volume. Now what is specific volume? It is volume per unit mass, correct? So if you find out for this system, the specific volume is V by M, right? And even if you find out what is the specific volume for this part or this, it will be again this half V by half M. So it will be V by M, and same way here also it will be V by M. So it means the specific volume is independent of mass. So it must be the intensive property, correct? So hello, are you getting my point or not? Am I audible?
Yes, sir.
Yes, sir.
Now see the difference between the extensive properties and intensive properties. In case of extensive properties, we said that the extensive properties can be function of time alone, whereas the intensive properties can be function of both position and time. Remember this. Intensive properties can be function of both position and time. So I can write the functional relationship like this. For example, these are the intensive properties. So I can say temperature is function of space and time. So let us say if I take the x coordinates, Cartesian system, x, y, z coordinates, then I can say temperature is function of x, y, z and t, right? Or for one dimensional case, I can write temperature is function of the space coordinate x and time t, right? Same is true about pressure and density. I can use this kind of relation because these three are the intensive properties, whereas the same philosophy is not applicable for extensive properties. So let us say if the volume is there, so I cannot write the functional relationship like this, that volume is function of space and time. No, this is incorrect. So volume may be function of time alone and not the function of space. Remember this. Is it clear? The basic difference between extensive and intensive properties?
Yes, sir.
So you cannot have the situation like the volume here is something like 3 meter cube and here it is 2 meter cube. No, not like that. It is not function of space. It is function of only time. At a given time t, the volume is fixed. No, it is not varying with space. Remember this. So specific volume, pressure and temperature are important intensive properties. So we will be using these values more frequently. So you should note on this. specific volume, we'll be using symbol small v, the pressure P, and the temperature capital T. These three are the important intrinsic properties which we are going to use widely here. Now, can I go to next slide?
Yes, sir.
Yes, sir.
Okay. Now, what is thermodynamic equilibrium, or what is equilibrium? You must have studied in engineering mechanics. What is equilibrium? What is equilibrium?
Net effect is 0.
So read the definition of equilibrium now. Thermodynamic equilibrium rather. A system is said to exist in a state of thermodynamic equilibrium when no change, this line is important, when no change in any macroscopic property is observed. If the system is isolated from its surroundings. So what you have to do is you have to isolate the system from surroundings, means it is not interacting with the surroundings, and under such scenario there should not be any change or there should not be change in any of the macroscopic property of the system. Then we can say that the system is in thermodynamic equilibrium. Clear? Now, what are all kinds of equilibriums you must have studied before? So, the equilibriums are basically of three types: the mechanical equilibrium, chemical equilibrium, and the thermal equilibrium. And these three combined together, if the system is in all kinds of equilibriums, all these three kinds of equilibrium, then by default it is in thermodynamic. So, this is how you can classify this. So thermodynamic equilibrium, so we have the mechanical equilibrium, which is nothing but the equilibrium of forces. We call it as equilibrium of forces. So when we will say that your system is in mechanical equilibrium, when there are no unbalanced forces present in your system, when there are no unbalanced forces. So for example, if you have a ball like this, which is resting on the ground, and it is in the position where it is right now. So don't you think this is a mechanical equilibrium? Is it? Or not? Do you think this is mechanical equilibrium or not?
Ball is at rest, so it is mechanical equilibrium.
So what is happening here is the self weight of the ball is acting in downward direction, right? And this is balanced by the reaction offered by this ground, right? So these two forces are balanced, no? So there is no unbalanced force present here. So you can think about this kind of situation as a mechanical equilibrium where no unbalanced forces exist. Now what about chemical equilibrium? So what is the criteria for chemical equilibrium? There should not be chemical reaction taking place. There should not be chemical reaction taking place, and no transfer of matter or no transfer of mass should happen, right? So the process like diffusion or the solution, you know, here there is a transfer of mass taking place, right? Or what you can say, the solute is getting dissolved in the solution, right? Solvent, and forming the solution. So these kind of processes, you cannot say that it is chemical equilibrium. So the minimum requirement for the chemical equilibrium is there should not be any chemical reaction, and there should not be any mass, any transfer of matter. Then the system will be in chemical equilibrium. And last kind of equilibrium is thermal equilibrium. So what we mean by thermal equilibrium is initially your system is in mechanical equilibrium, plus it has also attained the chemical equilibrium, and such kind of system which is in both mechanical and chemical equilibrium, you have to take that system and separate it from the surroundings by diathermic wall. So you have this system, you have to separate this surroundings by from the surroundings by diathermic wall. So diathermic wall is the wall which will allow heat transfer to take place, or heat flow will take place across the diathermic wall. If this is the scenario, then we call, and if all these criteria are met, all these three criteria are met, then by default your system is in thermodynamic. Clear? So in case of mechanical system, when the system is in equilibrium, there are no unbalanced forces. In case of chemical equilibrium, there are no chemical reactions taking place, no transfer of matter is taking place. And in case of thermal equilibrium, there is no heat transfer happening, right? So if you meet all these three criteria, then your system is in thermodynamic equilibrium. Clear? Moving further, we will talk about, or we will elaborate on this concept of the process. Now, what is process? What is process? For some time I explain. So this is your initial state of the system, and by any means, if any of the property of your system changes because of any reason, then it will acquire the new state, and whatever is happening from initial state to final state, we say that the system has undergone a process. So this is process, right? And if I show this path clearly, I may call it as a process path, right? So what we mean by this term quasi-static process? Any idea? Have you studied this in physics? What do you mean by quasi-static process?
Reversible.
No, not reversible. See, the name itself indicates. So static means you can think about nothing is moving or nothing is changing, something like that, right? Stagnant or at rest. Static means what? Correct? So the meaning of quasi-static is it can think of as an infinitesimally slow process. Infinitesimally means so a very, very, very slow process. Right? So we are going to talk about this kind of process, quasi-static process. Now look at the diagram on the left hand side. So what you see is simple piston cylinder arrangement is there, right? And there is gas enclosed in the cylinder. Here is gas, which is that the initial pressure, let us say P1. Now this is pressurized gas, let us say, and the volume, specific volume is V1, and this T1 is the temperature, right? And this gas is interacting with the walls of this cylinder, right? So this is your piston, and what is done is on this piston there is one weight, capital W, which is put on the piston, right? Now because of the force applied by this piston, this gas is compressed, and it is in the initial position where it is right now. So let us call this as the initial state of your gas or initial state of your system. So this part I am going to say this is our system. Fine, this is our system at initial state. Initial state. Now what you have to do is you have to remove this weight. You have to just take out this weight which is put on the piston. Now what will happen? Now as I already said, this gas is under pressure, means it is pressurized. So this gas will naturally expand, right? And the piston will move up, right? Up to what point this piston will move? So consider that the pressure of the gas is high enough. So this piston will reach this stopper, which is at the top. So this is your stopper, or the stops. So piston will hit here and will acquire this position. Right? So this is the new position or the final position of your piston. You can call it as this one, right? So what has happened is you have taken out this weight and then piston move upward, and then you stop at this stage, right? So let us call this as a final state of your piston, or final state of your system. So what we are talking about is the transition between the two equilibrium states by an unbalanced force. Now what is the transition here? See, the initial state, when this weight was present on the piston, this initial state was equilibrium state, nothing was moving, right? This piston was at rest, weight was there, and the gas was also at rest, nothing was moving. So this was the initial equilibrium state of your system, right? Then you lifted the weight, or you have taken out the weight, then you acquire one more equilibrium state, the final state. Now once the piston reaches the top here, now it is not going back, right? So it is at this level only. This is also one of the equilibrium state, final state. So these two are the equilibrium states, initial and final state. Now, why these changes occur? Because you have taken out the weight, right? So this weight is acting as the unbalanced force now. So you are taking the weight out, then the system is in unbalanced, and it will try to acquire next equilibrium state, right? The moment you take out the weight. Plot this on a PV diagram, how it will look like. So you should draw this PV diagram. So take the y-axis, take pressure on the y-axis, and then the specific volume, small v on the x-axis. So this is your initial equilibrium state, state 1, initial state. And this is your final equilibrium state, state 2. So write down the pressure will be P1, then the volume will be V1 for state 1. Similarly, note down what is the volume for the state 2 V2 and the pressure P2. Okay. Done. Now, intentionally I am showing this connection between state 1 and state 2 by dotted line. So I said I am doing this intentionally. I will explain why we are doing this intentionally later. Time you just remember I am using the dotted line for this. Now can I go to next slide?
Yes, sir.
See, this is how the process will occur when you take out this weight all of a sudden. See, natural process will occur in this fashion only, right? Get me or not? Now, what we have to do is, we have to do the same process but in quasi-static fashion or quasi-static way. It means we have to do this in infinitesimally slow way, right? So the problem with this kind of system is when you take out the weight all of a sudden, you cannot have the equilibrium states in between. Pay attention, you cannot have this kind of equilibrium states, or it is not possible to trace the equilibrium states in between. So you have only 2 points to look at. One is the initial equilibrium state and second is the final equilibrium state. Nothing else in between can be traced. So this is what happens in actual process. Remember this. Now we want to conduct the same experiment in quasi-static way. So what we are supposed to do? Now look at this diagram. See, what is the difference between the previous diagram and this one? There is only one difference. The difference is in get me or not? So whatever weight W you had in the previous diagram, now this weight I am going to divide in small weights, very small weights like this, and all those weights I am putting here. So see the equivalent of this you can think about in this diagram. So you have the gas or a liquid which is occupied here, and this is your piston, and on this piston you are using very small weights, these small weights. So the idea is you have to take one small weight out at a time, one weight at a time. Get me or not? So what will happen in this case if you take one weight at a time? So your system is following this quasi-static process. Whatever states in between states your system will acquire. Suppose if you take the first weight out, you will get this state. You take second one, you will get this. So likewise, you can trace all the equilibrium states in between like this. All these states can be traced. So provided you are using very small micro kind of weights, like weights are in, let us say, in milligram, such a small weights you are using. So you can trace all these in between states because every state is going to be equilibrium state. Is it clear?
Yes, sir.
So this is quasi-static process. That's why I said quasi-static process is infinitesimally slow process. Infinitesimally slow process. So draw the PV diagram, and now as I know each and every equilibrium state in between, I can join these 2 points by a continuous line like this, because I know the path followed by my system everywhere along this. So I am joining this by a continuous line. Yep. Hello.
Yes, sir.
Okay. Now I will give you the day in day out example of this quasi-static process. So even though quasi-static process is a theoretically very good process, you will find anyway you will find out in the coming lectures how good it is, but it is not practicable process. That is also true. So even though you may desire that the process should occur in quasi-static manner, but it is not possible in reality, or producing this kind of process in actual scenario is going to be difficult. Now how it is? So I will just ask you one example. How you fill the air in the tire or the tube of your bicycle?
By using a pump.
You know that pump? Hand pump? Right?
Yes, sir.
So imagine that process. So how you do it actually? How much time it will take? Maybe 2 minutes, 3 minutes, 5 minutes, something like that, right? To fill
Yes,
the air in that tube, right? Hardly 4-5 minutes are required. So that is also piston cylinder arrangement, or not? Correct?
Yes.
So in natural way, how you do that? So you just move that piston up and down quick, no? Or not?
Yes, sir.
So then hardly in 4-5 minutes you will be in position to fill that tire completely by the air, right? Now the same process, if you try to replicate using the quasi-static process, means what you have to do is you have to push the air inside the tube in such a way that each and every state in between attained by the piston cylinder arrangement is equilibrium state. Can you imagine how much time will be required to fill the air in that tube? Maybe 6
That
months,
will take
1 year.
a very long time will be required.
6 months or almost 1 year, right? Or
Yes.
not? At least 1 year it will take. And then you have each and every in-between state can be thought of as an equilibrium state, right? So that is problem with the quasi-static process. This is a very, very slow process. That's why infinitesimally slow process. So even though I said, now what is the advantage of this process? Process is, in reality you will see that the cylinder of that hand pump will become hot, right? Within 4-5 minutes,
Yes.
if you are pushing that air, within 4-5 minutes, that surface of the cylinder will become hot, right? But if you do this in quasi-static process, it may not happen, right? So this is a good thing about quasi-static process. But what is the use if you require 1 year, almost 1 year to fill the air in the tube? Do we human beings have that much time with us?
No, sir.
So this is the limitation of the quasi-static process. Even though it is good process, but in reality it is difficult to deal with this kind of process. Now you may raise the question then, why to study quasi-static process then? If that is the case, then why to study quasi-static process? See, we always try to compare our natural, our process with the best one, right? We always want to compare our process with the best one. So for that reason, you have to study this quasi-static process. You must know what is quasi-static process. Then and then only you will compare your actual process with this, no? Or not. So for example, this process may require minimum work input, right? Suppose it is power consuming device, let us say. Power consuming device. So you are giving some work input to the system to run that, right? So if you have this kind of process, it may require minimum work. So you can compare how close your process or how close your operations are compared to your ideal process, which is this quasi-static processing. So for that reason, comparison purpose, you must know what are all these ideal processes. Clear? Shall I go further, or we should stop? 5 minutes are there. If you want, I can cover 1 or 2 slides. Otherwise, we'll stop. Hello. Okay, what is pressure? Do you know what is pressure? We will cover this slide and then we'll stop. Note down the definition of pressure. Note down this. Bolo. Hello.
Yes, sir.
Now, what is pressure? So similar to density, the way we define density, we can define pressure also using the limits. So see the definition of pressure using limits. So P pressure is equal to limit delta A tends to the delta A dash, delta Fn by delta A. Now intentionally this is written as F to the base N. This N indicates normal. So those who say pressure is force per unit area, this is actually they are using it in wrong sense. You should not say only force per unit area, rather you should say more specifically normal force per unit area and not just force per unit area. That's why this F to the base N is written here. Right? Now note down this units of pressure. So we know the basic unit of measurement in SI system for pressure is Newton per meter square, right? So this is force, normal force per unit area. So force will be Newton divided by the area, which is in meter square. So Newton per meter square is the unit for pressure in SI system. And this 1 Newton per meter square is called as 1 Pascal. Write down this first one. 1 Pascal is equal to 1 Newton per meter square. Now there is one more unit for pressure, called it as a bar. So write down this relationship. 1 bar is equal to 10 raised to 5 Newton per meter square is equal to 10 raised to 5 Pascal, because these two are one and the same, is also equal to 100 kilopascal. So we have one more notation, one more unit for pressure. We measure it in terms of atmospheric pressure. So what is 1 atmospheric pressure? 1 atmosphere is, you can note down this value, 1.0132 into 10 raised to 5 Newton per meter square, or 1.0135 bar, or 101.325 kilopascal, one and the same. And one more unit is there, kgf per centimeter square, this one. So write down 1 kgf per centimeter square. Kgf stands for kilogram force. Kilogram force. So 1 kgf you will convert it to Newton in 9.81 Newton divided by the centimeter square. So this 1 centimeter square will be 10 raised to 4 meter square. We know this. So 10 raised to minus 4 Newton meter square, right? So this will go up in the numerator, so that's why this is written as plus. So write down 1 kgf per centimeter square is 9.81 into 10 to the power 4 Newton per meter square. This is also equal to 0.981 bar. So in short, you learn the units for pressure are Pascal, then bar, Pascal and Newton per meter square is one and the same, bar, then atmospheric pressure in terms of atmosphere, then in terms of kgf per centimeter square, and I am not talking about the English units here, so kgf per centimeter square. So laboratory gauges will read the pressure using this unit, kg per centimeter square. No? So note it down. Hello.